Hello, mentors. Welcome to Murals. So this is activity 1 from the meaning of Dembele art, part 2. And what do we want? So we want to explore symmetries now with colors, building on part 1, in which we just did black and white without any colors, just the shapes. So we want to add color to that. We also want to justify why having two symmetries is impossible. So in part 1, hopefully your students had this exploration about the two categories, and they just conclude, I see that no shapes have exactly two symmetries. Don't know why, but it must be true. So hopefully they got to that. If they didn't, that's fine. Part 2 will still kind of try to go towards that. And so that's the main purpose of this part, of this activity, Murals, justify why having two symmetries is impossible. So in teams, students will color a mural to achieve a different goal each time. And so here's the mural. There's several versions of the same. So the first is no horizontal, no vertical, and no rotational symmetry. So let me say that before coloring, this shape has all these symmetries. For example, if I rotate it 180 degrees, I actually get symmetry. Same if I flip it, right, in any axis, I will not change the shape. It's all the same. But if I color it, I will. So students should have no problem with that, zero symmetry. So this first part, it's very simple. They just want to pick colors kind of very randomly without any order or patterns. And that will take care of the lack of symmetry. Second, color it to have exactly one of the three symmetries, a pick. So they'll pick either this, or this, and they'll color. For example, they could pick only rotational symmetry. So they would choose this blue triangle to be exactly as this blue, because they predict that this blue triangle will travel to become this one. And the same way for this one. Here they do green, green. So things like that, right? Red, red. They could do all these for pinks. So it doesn't have to be all the time that they do differently. Black here, red, red. And when you do the half turn, you get the same shape. But if you do the flip, this x-axis flip, you can see that it fails, right? Because this red becomes this black becomes this red, and vice versa. So it just doesn't work. Same for the y-axis flip. So they just get this half turn. By the way, this was no symmetry, as you saw, very kind of random. And all these three moves produce shapes that are different to the original and also different between themselves. You can check. So the last part, it's the hardest one, and it's what leads to our reasoning. Can you have exactly two of the symmetries? Try. So they still try a little bit, but they already tried a lot with other shapes in part 1. So they don't have to try much, but just concentrate more on what's happening and why. So the hint is, okay, just try first to relate the three transformations, the two reflections and the half turn. How do they relate to each other? And that's a difficult question first, because what do you mean relating to the three moves? And then you can ask them more guided prompts, such as for example, do two of them. What do you get? And they will see that kind of magical things are happening. So let's summarize this. If I do a vertical axis flip and then a horizontal axis flip, I get a half turn. Again, they can discover these formulas, this kind of called algebra of transformations or algebra of moves. When I do this composed, so this sequence of two moves, I get that one. How to prove it in the meeting? So we want you to be using X, Y, or pairs or abstract things, but more visually. We'll place the center here. We'll work with a random shape that's supposed to be any shape. And we'll pick a point, okay? And we'll draw a point, and we do a chase diagram. So that means chasing the point after what happens after each time. So the first is the vertical axis reflection. It sends it to the other side, right, of these two planes, the right part and the left part. So it sends it to this part. And then what happens when I do the horizontal axis reflection? Well, it sends it down. And then the question is, if I do a half turn, students should have like an aha moment that tells them that it also does these two together. It sends them down right away. So it's like a fast way of doing these two in that order, right? So a half turn visualized as a two-step move. So you follow the red dot, for example, and they could pick another dot, like here, a dot here, and do the same chase and see that it's the same as reflecting. So the intuition is like this. Anytime you do a reflection, of course, you kind of twist. It's like taking a whiteboard and just flip it. So if you do two reflections, even though one is vertical and the other is horizontal, you kind of get back to the same whiteboard. So you don't flip the whiteboard, but some price had to be paid, and that's rotating the whiteboard 180 degrees. So I want you to do an experiment right now. So just stop watching the video, but just take a look at your hand and just place it so that you see your fingers and your nails, for example. Do a vertical axis flip. So just flip your hand, and now you see the palm of your hand. Now do a horizontal axis reflection. Okay, it's kind of hard. Don't get injured, but just flip it up down. So now your fingers should be pointing down. And now realize that what you did was just a 180 turn, right? 180 degree rotation. Because if you do it, you'll get your hand again. You could do that with your hands or with other shapes, like physical objects during the meeting, to get your students see why this is happening. So again, it's not about the formal proof, like take and pair X, Y on the axis, and then the coordinates becomes minus X and things like that. You don't need to do that. You can with some students. That is more to taste it, to have a good intuition and convincing on why this is happening. And that's the intuition, that two reflections get you back in shape in the terms that you didn't reflect. You get the same face somehow, but you had to pay a price, and that price was rotating around. What's pretty cool is that if you just change the directions of this to this, and students would need to justify why, you also get new equations that are very similar, that tell me that two different moves are equal to the other move that you didn't include it here. So half turn plus V axis flip is equal to the H axis flip. You could also do it with your hand, do a half turn with your hand, and then do a vertical reflection. You'll get the same as if you had done a horizontal reflection, horizontal axis reflection. Same here, horizontal axis and a half turn become a vertical axis flip. So that's pretty impressive, in my opinion. That's pretty cool. Another cool thing you could ask your students is what happens if you do the three together. So the three in a row, and let's try to do it. So at this point, once your students are convinced about one of the equations, no matter which one, let's say, for example, they convince of this one, then they can generate all others in a very nice way. Let me show you how. Let's say your students up to this point really believe and visually understand why a vertical axis followed by a horizontal axis flip equals to a half turn. You could then ask your students the following. What happens? What if we do all three? So we take a shape and we do a vertical axis, then a horizontal axis, and then a half turn. So this part is about applying all knowledge, applying all theorems or all results to generate new information. So this is what students will be doing at this point. They'll say, look, we already know that doing a vertical and a horizontal together, like one back to back, give me a half turn. So this is actually equal to a half turn plus a half turn, just because of the first part, right? But then it's easy to see that 2 half turns is just full turn, but a full turn, 360 degrees, is just the same. So the final result is that doing this is equal to nothing, doing nothing, or you could also say the identity move, which is do nothing to your shape, don't do anything to your shape. So we have a nice equation for that. Other questions, what happens? So like the question is, the order matters? What if we do other things? So for example, let's just erase this here for now. So now we have these two equations. But what if we do first horizontal axis, flip, then we put the half turn in the middle, and finally end with a vertical flip, right? What's going to happen? And so you could, for example, know that if you do this, let's see if we can have this here. Yeah, you could say something like this. Okay, I don't know what it is, but this is some monster. This is some shape. This ends up being some shape. And then you could, for example, say, if I do a vertical axis flip to both sides, so then it's gonna be like this. So you kind of do it to both sides. So we're just doing algebra somehow. We do it here. So our mission is to figure out what this XXS here, right? What is this transformation? So we say, hey, let's do a vertical axis flip again. So it would look like this, doing it 4 times here. And here to the right, it would look like doing just one vertical axis flip to whatever this is. Okay. But we know that vertical plus horizontal plus half is doing nothing, right? It's the identity. So we can actually erase this because it's just doing nothing. And we just get that vertical axis. If we do a vertical axis to something, it's the same as doing the vertical axis to this. So it takes you some convincing to say that, to conclude that this is just nothing. So this is just the identity. So we get another equation that tells me that the order here really doesn't matter, and you could get the same one. I guess the final thing that I would probably say is that if we repeat, what if we repeat? For example, if we do horizontal axis and horizontal axis twice and vertical axis, then they can see that this is not the identity because 2 horizontal axes together, back to back, just kind of cancel each other. And then you just get the vertical axis flip. So you have to have the 3, but just once each. Okay, what do we do with these equations? Well, what happens then is that we will conclude that we cannot have exactly 2 symmetries. And let's go back to our shapes here. The thing is, if we had 2 symmetries, for example, half turn and x-axis flip, then when we do the other one, we would know that that other one is just doing the other 2. But since doing the other 2 don't change the shape, then if you do them together, you also don't change the shape. So the fact that this shape would be fixed by 2 of the symmetries would imply that the other symmetry is also fixed, right? It also happens. So 2 lead to 3. So that would be the other result. Because 2 fixed lead to the last one. So the remaining one also fixed the other move. And that's what students should be concluding. Let's summarize what's going on here. And this is a summary for the whole meeting, really, because it starts from part 1. They first try examples. They try a lot of examples to feel that it's impossible to have exactly 2 symmetries. Then they say the main conjecture in their own words. So there's many ways to say it. If you have 2, you have 3. You cannot have 2. You either have 0, 1, or 3. There's several ways to say it, but all should be saying that impossibility. And then in part 2, you would still come back to this conjecture because we're still asking them if you can 2. So they didn't get rid of this. Now they explore it more in depth. And they will say a conjecture number 2 relating the 3 moves. And here are the conjectures. There's several of them. So either it's fine or they can actually produce the 3 or even more, as we saw. It just becomes combinatorics and a lot of algebra there. And they justify conjecture 2 visually. This is what we did. And then they use conjecture 2, so either of these equations, to conclude the main result, the main conjecture, that you cannot have 3. So this is the logical path or the progression that we're doing with your students. First, they're analyzing. First, they're doing example. They're analyzing. Then they're making conjectures. And finally, they're actually justifying and proving. So if you go to these, they're analyzing first to this diagram of the teaching guide. They're first analyzing. They're searching for example, predicting cases. They're noticing common properties, repeating patterns. Then they're generalizing. So they're explaining things that happens and they're communicating in some rule or record cases, etc. And finally, in part 2, they're justifying, right? So they're using logic, or they're verifying, or they're starting a logical argument, or describing what they did, etc. So it's a logical progression, mathematical logical progression that happens in the meeting. There's many access points, as you saw. It's very visual, so you don't have to stay this level of abstraction really, but just point to that. You could start if you want, just if your students are a little puzzled in this, you could just start with these equations. What's a vertical axis plus a vertical axis? So what are 2 flips equal to? And they could get to saying that it's doing nothing, so it's the identity. And then go from there. It's pretty cool because it's connecting algebra with geometry. So we have a lot of geometry, a lot of visuals, but we're now writing equations for different transformations. So we hope you enjoyed this part of the meeting and see you in the next video. Goodbye.